Hello everyone. I think we are live.
Okay. Hello. Hello everyone. So this is your open session for week 8 and week 9. So if you have any doubts related to week 8 and week 9, you can ask. Hi Srinivasan. Hi Shekhar. Do you have any specific doubts?
Hello, good morning, ma'am.
Oh yes, good morning Shekhar.
I have doubt in week 8 for the convexity set activity question.
Yeah, please ask. Can you tell the questions number or what exactly?
So activity question 8.4, question number 1, where we have to select the option for the range of lambda.
8.4, question number 1. Let me check.
Jimmy, shall I share my screen so that?
Yeah.
Okay. The screen is Shekhar, which question you want to have?
Ma'am, 8.4, question number 1.
8.4.
Okay. Yeah, tell exactly. So according to you, what should be the answer?
According to the lecture, answer should be 0 to 1. Right.
Yeah. See, this question is given to just confuse you. In the question, according to the lecture, sir has discussed about a property. Like if x1 and x2 is 2 point is there, and there should be a point x3, which should always lie between in between the x1 and x2. But here the question says, given S is a convex set in R square, and x1, x2, x3 already belongs to S. So in the question itself, it is mentioned that x3 belongs to S only. Okay. So in that case, the question is asking what can be the lambda value. Okay. So I'll show you by the picture. Ma'am, it's better I have to show my screen. So
Okay, I'll stop sharing.
okay. Is my screen visible?
Yes, it is visible.
Yes, sir.
Yes. In that case, just think about a picture like this, okay, or any picture. I'm just looking at a triangle only. See, let's say this is x1. Okay. This is I'm just think as x coordinate and y coordinate. Okay. So let's assume here is your x1 point. Okay. And this triangle is your convex set. So convex set S it is, and just estimate this is your x1, and here is your x2. Okay. So what the definition says that if we take any 2 point, then in that case, if we take any point, 2 point, let's say x1 and x2, then in that case, it should satisfy this equation. Okay. If we take any 2 point, then in that case, x3 should also be lie in this set only. Okay. That our definition says. But in this question, it is already mentioned that x1, x2, x3 all belongs to this set S. Okay. So let's say x1 is here, x2 is here. Okay, x3 can be at any place. We will take two cases. In the first case, it should be here. Okay. X3 is here. In case 1. Okay. And suppose in case 2, x3 I'm taking here. I think I should take some other color. Okay. So till now, are you with me? Hello?
Yes, sir, got it.
Yeah. Let's discuss about the case 1. Okay. And we will take some values for our like x1 should be 2, x3, x1, x2 should be 3. Okay. So in the first case, what would be our x3 value? In that case, we are taking lambda value as between 0.5. Okay. Just less than 1 according to the definition. Okay. So if lambda value is 0.5, then 0.5 into 2 plus 1 minus 0.5 into 3. Okay. So it should be 1 plus 1.5. Okay. And 1. It should be 2.5. Okay. It comes around 2.5. So according to in case 1, x3 comes here. Okay. And you are satisfied with the point like it should be value between 0 to 1. Okay.
So,
Hello?
so this option should be correct, right? Lambda belongs to 0 to 1 should also be correct.
But that option says well, lambda should be always between 0 to 1 only. But I will show you that lambda can be more than 1 also. If actually it is just a confusing question because people used to get confused by seeing the definition. Okay, but it is something different from the definition. See, if what will happen if in this case like here, if x3 is there, still it is in this set, no? In this set. Okay.
Yes. Okay.
Yeah. Then in this case, just see. Here we will take lambda value as 2. Okay. Yeah, 2 or 1.5, anything more than 1. So if we take 2 for our easy calculation, 2 into 2 plus 1 minus 2 and x2 is 3. Okay. So 4 minus 3. Yeah, it comes around 1. Okay. So actually this is the case where lambda is at this place. Okay. So still you are able to see that if lambda value is more than 1 also, still the x3 value can be inside this set. Are you getting my point?
Okay.
Yeah. So the definition says that if you take any 2 points, then and if you take lambda value between 0 to 1, graphically it means that if we take any 2 points, then all the point in between these 2 points should lie in this set only. See, if we take these 2 points, then all the point in between this should lie on this line, inside this set only. Okay. But here the question says like we take 3 points there, x1, x2, and x3. If x1 is in this set, x2 is in this set, and x3 is combination of these 2 points. Okay. Then is it necessary that lambda should be 0? Lambda should be between 0 to 1. Then only this point will lie in this set. So this is the question.
Okay, sir, got it.
Anything else from Wicked?
This is Srinivasan here. Did we have the week 9 solve with instructor session on Wednesday evening? I did not attend. I don't see the YouTube link.
Yes, Srinivasan sir, actually, no one joined for the session. We joined the session live, but we waited for around 20 minutes. But since participants were not there, we had to close the session.
Okay. Yeah. So people do say that they watch the videos. So is it because I don't have that many open questions on week 8 or 9, but
Okay.
would it be possible for us to request to have that SWA session now? And maybe if it is okay with you.
See, since we cannot run the session ourselves, no, that's why it was late.
Yeah, I understand. Yeah, that time I understand. But is it
Okay,
possible
okay.
now? I don't know who else is on the call.
Solve with this instructor. Actually, what happened is that day we have activity and practice also.
Okay.
Do you have any questions in activity or practice?
Of week 9, I don't have.
Yeah,
I think.
don't have.
No, I haven't attended the practice session, so I should not claim that.
Okay.
Activity, I don't have any questions. Activity, I don't have any questions. So.
Okay, I see. What can we do now? Jimmy, is it okay if we go with solve with this instructor questions for the week now?
Or again, whatever. So, or okay, let me put it that way. Whatever your plan on Wednesday, if it is okay with you, if you can do it now, that could help others.
Okay, Jimmy. So, Shaker, is it okay if we go with week 9 contents?
Yes, absolutely, ma'am. I don't have any.
Okay. Okay, Shimaz, just give me a minute. I'll open it and then I'll share the screen.
Okay, thank you so much.
Okay.
Hey Srinivasan sir, how was your quiz 2?
Quiz 2, I was quite happy with that part, but I have to check the marks. So the marks doesn't seem to be as much as I expected. But I think the paper 2, right? And then the PCA questions seemed too simple. I was surprised that the answers were simple. That is what I had the biggest doubts before that, and I felt quite happy with the overall thing of quiz 2. And even the earlier week question, I felt that what was in quiz 1 you didn't cover it, you covered other things in quiz 2, so it was a good match, right? And I did not accept that kind of a question on SVT. The SVT question I couldn't solve. Actually, I couldn't figure it out, and the quiz 2, the other papers also were lengthy. Right? So
SVD questions were conceptual.
Conceptual, yeah. So, so I couldn't finish it. I guessed it only, but I didn't get that answer. So I think it was probably should have gone and read. That is very interesting. Even the conceptual question is interesting, right? Because you can't cap, like the PCA question ends up being, even the SVT questions, right? Unless you make it multiple choice, they end up being split into multiple things. It is difficult to do with SVT. That was just nice. But I found the balance quite nice. So
yeah, we wanted to make the paper workable. That was the thing.
Yeah, and if people had got 90, I didn't get 90 plus, but if people had got 90 plus in that paper, it will be a good test of their grasp of those topics.
Yeah, actually, easy papers are sometimes more trickier in terms of scoring marks.
Yeah. the thing I have to check whether what was the mistake I made because the LSC, the linear regression, that thing was very simple, right? The question was reasonably simple, except that more data points. And there I don't seem to have made some calculation mistakes, right? So I'll have to go check that.
Yeah, okay. What about Shekhar?
Yes, sir, it was nice. I also made this. I also made mistake in that linear regression problem. The calculation was very lengthy. Also, our calculator is not that much good.
Yeah, for this calculator issue, we have to put it before our team. Let's see what we can do with it. But you have to deal with it for now.
Yeah. The biggest thing is that square root in that calculator is somewhere else. So every time I forget where the square root is. So
it also works differently.
Yeah.
Like from our normal calculator.
Yeah. So
yeah, and we are hearing a lot about this calculator.
See, no, yeah. What happens, Abhinand sir, is that you have to use mouse to click everything, right? So if I have to put say 23.1235. It takes tough effort because those mouse are not very good. They are not. I mean, they are not that quality because they've been used so often, right? And
but actually, you know what? In competitive exams, also they don't allow keyboards.
Yeah, they have that. I don't know how this thing, but the calculations I don't know how what they're. I actually have to check with others also. But the more digits you have in the calculations, more liable for you for mistakes.
Yeah, so this time thing, we have to time the questions properly.
Yeah,
that's the thing. But again, this keyboard is not allowed in most of the competitive exams.
Yes. See, for example, that divisional derivative, I know it was straightforward. I don't know whether I got the marks, but definitely I don't seem to have got the marks on that. So that is a directional derivative, is a straightforward multiplication, right? So there, that questions of making data entry mistake in the calculator are high. But that's okay. That's what we are living with. I think anyway we have been using it for 3 terms now. We have to get used to it.
Yeah, I mean, we have to do improvements, but for now, whatever is there, we have to deal with it.
Hello?
Yeah, ma'am, you are audible.
Okay. So if you are okay with the activity and practice questions, then this is all of this instructor session. I didn't prepare much yesterday because as it was a full complete session with the activity, practice and solve with the session.
Yeah, ma'am, one thing I want.
Yeah,
ma'am. If week 9 people have not covered yet,
yes.
Do you think solve with instructor they can solve questions?
Okay. So practice problems. Have you taken a look, Srinivasan and Shekhar?
No, I have done the activity because activity I generally have this habit of watching the lecture and finishing the activity question immediately. But the practice session I have not come. I didn't get the time. I actually wanted to do it in the last 2 days, but I didn't get the time to finish it.
Okay.
So we can go with the practice. Yeah.
Okay, then shall we go with the practice session and then?
However you want to do it. Yeah.
Srinivasan sir, I think solve with instructor will be better served if you solve it. So will you be able to solve it now with ma'am?
Yeah, definitely. Because I've read that part. I've gone through the content. I just haven't practiced it. Yeah.
Okay. So ma'am, you continue with whatever you like.
Okay. So solve with this, I have not taken much solvable questions. I mean, that's related to concept oriented. We shall go through that practice questions once with their solutions, and then we can come back to solve with this instructor session.
Yeah, ma'am. So your call, totally.
Okay. So these are our activity questions. So in the first part, do you have any doubts related to this convexity and any functions about the composition of convex functions? Is there any doubts related to that? Mm.
No, the fourth one was a tricky thing, right? It has to be because it can be a convex function, can't be, will be,
Yeah.
right?
Yeah.
Right. And so that concept, so basically G has to be strictly increasing,
Yes, correct.
right? That's the right answer, right?
Okay, that's the correct answer.
Yeah. If it is G is strictly increasing, it will be a convex function. Otherwise,
I
it
think
can be a
F
convex
should
function.
be strictly
Can,
increasing.
Oh, okay.
It can be a convex function.
Yeah.
F should
okay.
be strictly increasing.
It should be, yeah.
F
F is both the convex and increasing.
strictly increasing. Okay, thank you for
and
that.
For second, I think G should be linear. Right, ma'am? There were
This
two conditions.
For
No,
third question, ma'am, Abhinandan, you're talking about third question.
Yeah, I mean, ma'am, there were two conditions for compositions to be
Yeah,
convex.
these are the two questions. No? Second question, third question.
Yeah, ma'am.
Yeah, he was asking about the fourth question. If F and G are convex, then
Yeah.
then composition F of G.
Yeah, ma'am.
Okay.
Yeah, okay, thank you.
Okay.
Yeah, sir, the lecture G being linear was not mentioned. At least in my notes, I just left it as G is a convex function from RD to R.
No, there are two conditions. You check in lecture.
Okay.
One is F is increasing, and the second one is G is linear.
G is linear. Okay.
Yeah, there are
Here
two
and then the lecture. So additional property. No? The first property is F is from R to R can be convex and non-decreasing. So this is the first composition here.
Yeah. And then G is a convex.
G is a convex function. But in the second case, we had that F is convex and G is a linear function. So that's why we have this equal to symbol here. It is equal to F of G of lambda x plus 1 minus lambda into y.
Okay. So then, so in this case, then if to get my clarified understanding, if G is convex and F has to be one case is F is convex and increasing, non-decreasing, and then G is convex, F of G is convex.
Yes.
If F is convex and G is linear, convex or otherwise.
Linear case. G is linear.
F of G is convex.
Can be both
concave or convex, right?
Yeah. At this case, since F is convex, we have finally we will get a less than value.
Okay.
So at that time, the composition becomes convex.
Okay.
So the screen is completely visible, no? Or do I have just
yeah, it is visible. Yeah.
Okay. So any other doubts in related to this activity? So let's go more quickly through other activity. Okay. So here it is simply the applications of optimization, that is linear regression.
Yeah.
So what is our performance measure? It's half WT, of summation over WT.
Yeah, WT. Yeah. And then the half, sir said that it is just a scaling factor and didn't give a particular reason, right, for that. Okay, I hope that there will be some other reason somewhere else. Okay. Yeah.
Since now when we go for deriving that loss function, there at that time this half gets cancelled when you take the derivative.
Okay.
So for mathematical convenience, we have this half.
Okay.
The second is, so this is our in linear regression, our sum of squares is convex function. So we have a proof also.
Yes.
That W transpose X into YA minus YA, we have that H function. At that time, we get a composition with the convex of convex, a linear function.
Yeah.
So it is a true statement.
True statement, yeah.
And the gradient is which equation? The gradient of the sum of the squares. Is it A, B, or C?
W into, okay. Sorry, I had to look at the notes actually.
Okay.
It's a conceptual thing, but I think I've written definitely in the notes, and then it is.
X transpose X into
W minus W. Yeah, X transpose X. The first one, right? That is the.
Yeah, first one is the correct answer.
Yeah.
And for this is
that
analytical
we derived it in week 3 also, right?
Yeah, we derived it in week 3 also.
Yeah.
The same equation.
Same equation. Yeah.
First equation.
Yeah, there's again the first one that converse.
X transpose X inverse into multiplied by X transpose.
This is just from the 3, right? You just take it the other side. It is 3 and 4 are basically the same, right? Yeah.
And this for pseudo inverse calculation, we have that order in terms of DQ.
D3, yes, that's right. Yeah.
And this is also the direct equation, substitution of that gradient equation here.
Yeah.
Answer is A. The next iteration is WT minus your learning rate multiplied by your gradient.
Yeah. And then one thing the sir didn't mention here is that if the steps, right?
Step size.
Yeah, in XTX and the XTY can be calculated ahead of time and kept. They don't change in each step.
Yeah, they don't change in each step for gradient descent as we take all data points as such.
Yeah. But even otherwise also XTX, he didn't cover it. He talked about taking a fewer points, but that is a question I had. See, because XTX is from the input.
Yes.
X3, X transpose Y is also from the input. So we can, however,
it is simple gradient descent, no? But what happens when stochastic gradient descent comes? Not for the next.
No, ma'am. Let me clarify this point. So even if you're doing a full gradient descent, I want to ask that XTX and XTY I can calculate in the first step and keep it aside. Those values I don't have to recalculate.
Yeah, those values will not change. Yeah.
Only the multiplication with WT, I have to do it for every step.
Every step, correct. And which of these holds for gradient descent and stochastic?
Yeah.
Of course, so all of these answers are correct.
Yeah.
Okay. And also, which of these holds only for this stochastic gradient descent is?
Yeah. So
here only the first.
Is it uniformly at random? That was very confusing. This now when I read it, I chose the first one.
Okay.
But is it uniformly at random? What does uniformly at random mean? The same number of points. I mean, I take the
same set of data points. So actually, sir wanted to have it like this way. Means if we consider, say, a mini batch size of 10 means. Uniformly, you sample 10 points like that.
Yeah. Okay. What are the other way I thought was that if suppose there are 1,000 data points, I pick 20 in each iteration. That 20 number I don't change. Which 20 I pick changes randomly.
Which 20 you pick changes randomly. You will not do it sequentially.
Okay.
So that's what we wanted to have.
Yeah.
It is at the same number but with different data points.
Yeah. And
the second is false. No, it does not follow the same pattern.
I felt that, but I couldn't get a proof of it. I don't know whether it will follow a different path.
Okay.
Sometimes but that's why I left it anyway. I chose only the first one. That's what I chose, and then that turned out to be right. But that's okay. That's conceptually. But anyway, I think today we don't have to discuss that. It's okay.
Okay.
Because the third point, particularly, whether it will take more iterations or not, I wasn't sure.
We are not sure.
Because you could take more iterations, right? I wasn't sure.
Third option is also the correct one. The stochastic gradient descent will take more iterations compared to the gradient descent.
I wasn't sure. I may be able to think of some cases where it takes fewer iterations, but I didn't.
Okay.
That's okay. I think these are more higher order concepts, right? We don't need to know them for this course, probably. Yeah.
So the next MLT course, we will visualize it more graphically. At that time, we will get to know how the step size changes and how we get to converge.
Okay.
And asking about the KKT conditions.
Yeah. So minimum this thing. Okay. This I have to.
This is related to supported permissions.
Yeah. So there is no WI, right? Yeah. Okay. We have to
sorry. I just skipped it. This is about the duality problem. We have that duality conditions, how we get strong and weak duality properties. So here you have a function, no? J of x, taken directly from our video lecture. No? This
Yeah.
function
So
has a
this is the
constraint
primal
h of
problem,
x.
right? Yeah.
Yeah. So for that, you have to, when you have an equivalent Lagrange function, its value is less than or equal to j of x.
Yeah.
So actually, it is a, is this a true statement or false statement?
That's a true statement.
It's a true statement.
Yeah. That this is the primal problem. The other is the dual problem. Yeah.
Yes. And for weak duality is a condition where your dual optimum value is less than or equal to primal optimum. So it is a false statement.
Yeah. Yeah.
And so for a strong duality to hold, what we must have both the objective and the constraint to be convex.
Convex.
So
Yeah.
this is the second.
And then in the tutorial, I think you described it in a graph. I don't know who.
Yeah. Yeah.
If the graphs meet, then it is a strong duality, right?
Yes. If there is no duality graph, it is a strong duality.
Yeah.
And these are the KKT conditions. Actually, for the second option, we need to make a change here. So first option is correct. Your del f of x star plus lambda star del h of x star is equal to 0.
Yeah.
And for the second option, it should have been like lambda star into h of x star.
H of x star, not del, right?
Yeah, del should.
Del comes only in the first condition, no?
First condition. It is only for the stationarity condition.
Yeah.
Your gradient we take.
Yeah.
This is for your second condition. No?
Yeah. And then third and fourth are not
Third
correct.
and fourth are not correct. And this is a primal feasibility. So
yeah. Fifth is correct. Last is correct.
Last is correct. This is dual feasibility. So the first is your stationarity condition. Second is your complementary slackness. And the last, and this is your primal feasibility, and lambda star less than or equal to 0 is your dual feasibility. And there's one more again, some testing conditions. Which of the following is a primal feasibility? For your primal feasibility, it's just taken from your constraint equation where your HI of so for primal means what value will be having x or lambda?
X star and lambda star, no? So X,
X is for your primal.
Yeah, X is for primal.
So HI of x star should be less than or equal to 0 for all I, and MJ of x star should be equal to 0 for all J. That is your primary.
So that is the second point. This is the second one.
Yeah.
Okay.
Second option is the correct answer.
Okay.
And for last one, which are the following here? KKT stationarity condition. So here also the option C is the correct answer.
Yeah.
Previously it was given as 2, and so we will resolve it.
No. Okay, and ma'am, this is actually very interesting part because I answered the activity question immediately after the lecture.
Okay.
And this lectures were so conceptual, right? So at that time I could get them easily. Now if you look at all of them together, all of them seem the same.
Okay.
So this is actually quite tricky to solve, right? Now I am looking at it.
Yeah. So these are also once after. Sometimes if you watch means if you try to.
Yeah, you will make that mistake. Yeah. So the second is actually without the del. Obviously del has to be there. Yeah.
So we have to, for the stationarity condition, what we do is we take the partial derivatives, the first order partial derivatives, and then we like a simple equation when we try to find a minimum of a function, what we'll do, we'll get the first derivative and then we'll equate it to 0.
Yeah.
So like the same condition we have for this stationarity condition. And for the seventh question, so we are having this complementary slackness condition. So which will be true? It is tricky, no? It is ui into hi of x star is equal to 0. So that is your KKT complementary slackness condition. So for that condition to hold, which value will you choose?
Either of that should be 0, right? The last.
Yeah. Either because there is no restriction that ui has to be 0 or hi has to be 0. So these two options will go off, okay? Because it says that ui star should be equal to 0, but that is not our dual feasibility condition.
Yeah.
It can be less than or equal to 0. So at that time, either ui or hi should be 0.
Yeah.
And this is a simple case where since it is already given as equality constraint, at the primal optimum solution x star is greater than or equal to 0. So the statement is false because
Plus,
it
it'll
is
be equal to 0.
equal to 0. That's on good KKT. And so when in SVM, not much concentration is given for SVM as it is for your ML techniques, right? So a simple understanding is given in our lectures for supported retention.
Okay. So how
So our
are they?
optimization.
Yeah, go ahead.
Yeah.
No.
So for our optimization problem in SVM is we have to minimize your half of that W norm square.
Yeah. But WI norm square, no? So that way WI was missing in all of them.
Yeah.
And then I couldn't figure out how 1 and 2 are different.
Here it is 0 is not included, no? But here it is 0 is included.
Oh, okay.
That was
So first one is equal to 1, right? That's what I have.
it should be equal to
greater than equal to 1. Okay.
It's not a 0. That's why these two options are.
Okay. But it should also be WI square, right? So, but I was not mentioned in any of the options.
Okay. Let me check it once. So actually, it's W square. It's when you take a norm value, if you put it in summation, it will have WI.
Oh, okay.
Since I have written it's a norm square, no? That's why it's in
WI square.
on the whole
Same.
it is W.
Okay.
Yeah, the same. So your objective function of SVM is
Quadratic, right?
Quadratic. Yeah.
And the constraints are basically linear.
Linear. So that's why we have it as SVM is used for linear constrained optimization. So that is a true.
True. Okay.
So let's move on to practice questions. So have any of you attempted this practice question, both of you, or not attempted?
I have not attempted so far, so I have to do it now. So this I will definitely just write the graph and then do it.
Okay. So what about you, Shekhar? Are you there? Okay. So Srinivas, since you are only here, Shekhar is right. For practice questions,
we could probably discuss the solution. I think x equal to -3 is
Okay.
function is in that thing it is decreasing, right? That's what I guessed it.
Okay, then I will show you the solutions. So we have a question like, so we have a function f of x equal to -2x square plus 5. So at x equal to -3 is f of x increasing or decreasing.
Okay.
So what is our, how can we check whether a function is increasing or decreasing? So if we consider the first derivative of f of x.
Yeah.
So at any point, so we have mentioned the point here, right? -3. So if you substitute the point at the derivative's value, if you get a positive or negative, based on that, it is increasing or decreasing.
F dash of -3 is 12. So in our this thing, R is 12, right?
Yeah. So here it is -2x square plus 5. So it is -4x will be your first derivative value. So when you substitute x equal to -3, what happens? It is 12. So it is positive.
Yeah.
So it is increasing function.
Okay.
For the second question, same. We have to find the global minimum value. So when does the global minimum occurs? In
Same
lectures also we have seen. We take the first
derivative is 0. Yeah.
So we equate it to d 0.
Yeah.
So at the simple value, so at when x is so this is the equation when you derive f of x to equal to 0. So you'll get 4x minus 1. So -1 plus 4x equal to 0. At that time, x is equal to 0.25.
Yeah.
That's your answer.
Okay.
So this is we have two convex functions, f of x equal to x square and g of x equal to e power 3x square. So we have to choose which is the best combination. So what are the two possible combinations that we are seeing in our lectures?
One is obviously sum is definitely a convex.
Yeah, sum is definitely a convex. So this h of x, that is x square plus e power 3x square. This is also a convex function, right?
Okay.
And another thing is when you multiply two convex functions, x square multiplied by e power 3x square, that will also be a convex function.
So we didn't cover it in the lecture, but I think it is can be derived from first principles.
Yeah, it can be derived. So therefore these two are convex functions, multiplications.
Okay.
But if you divide or if you have any subtract your any two convex functions, at that time you will not have, I think, that inequality constraint will not be satisfied. So that's why the subtraction and division are not giving you convex functions.
Yeah.
So this is actually two functions. G of x is 2x minus 3. So it is a linear function. And f of x equal to x minus 10 ln of 5x. So if you plot it, you get a convex function.
This
So
I couldn't.
simple.
Okay. Oh,
Yeah.
only by plotting, right? By just looking at it, I can't figure out whether why it. Oh,
We
you have to
cannot
look at-
figure, no, we have a logarithmic scale function, right? Ln,
Yeah.
natural ln.
So the thing was, ln ln 5x is a convex function because
Yeah,
E is a
yeah.
convex function. Even logarithm is a convex function, right?
Okay, okay. So this turns out to be also a convex function. This f of x minus 10 ln 5x.
Yeah, but I'm just trying to ask them. So see, 5x
Okay,
is a
okay.
convex function.
Yes, yes.
Ln 5x is a convex function.
Oh, so x minus.
Because there's
10.
if it is plus, I know it is a convex
Oh,
function.
okay,
If it is
okay,
minus, I wasn't. That's where I'm not sure. What do you?
Okay, okay, okay. So I plotted this, but I somewhere missed it. Shall we try to plot it once?
Yeah, we can try. Yeah.
So we have that.
X minus ln x. Yes. That.
So ln x, if you see here, is so that is our function. No? So
Yeah.
10 minus x minus
10 ln x. Okay.
So this is g. So can you see the g function here?
Yeah, that is okay. Okay.
So your ln x is not a convex function. Ln x
It's a okay.
It's a concave.
Okay.
Yeah. So x minus 10 times your ln of x. That gives you a convex function.
Okay. So the 10 is just a factor, right? I think anything would still
Yeah,
give.
10 is, yeah, anything is good. So we can also go ahead and remove that 10. So that also you get a convex function.
Okay.
G is still a convex.
Okay.
See, this is a negative function. See, concave, no, it is decreasing. So when you are subtracting it from x, no, so
It'll increasing. So
x minus, so negative of negative, it becomes so positive.
So is it something that we can apply all the time? If you take a negative function, if you take a concave function, suppose G is concave and F is convex, F minus G, will that be convex?
F
Always?
minus G, no, actually, if you have, say, F is a concave function, minus of F is a convex function.
Always?
Always, sir. In sir, lecture also, sir has proven. If you have G of X as yeah.
Concave.
So if you take minus of that function is a convex.
Okay.
So that's how even in lecture also, sir has
mentioned. Okay, let me. I'll probably have missed it. Okay, I'll definitely look at that. Okay.
You can verify the lectures.
Yeah, my thing was to go to look at the AP of it and then see it. Yeah, it will come out as negative. Yeah. Okay.
Okay. So we have that. So now we can imagine.
Yeah. So
now we have. So we can also plot it. So g of x is 2x minus 3, right?
Yeah. That is a linear function anyway. Yeah, that is going to be, so FOG is definitely a convex function.
Convex function. So no need to plot it, no? Shall we plot it?
Yeah.
G equal to 2x minus 3. So this is your G1.
Yeah.
So your convex your H is equal to G. So your F is, I have taken as G, okay?
Yeah.
G of G1. So this is your F, can you see?
Yeah.
H. So this is a convex
function. Yeah.
So this, I think you have to work it out. So
Okay,
given
probably
you
not.
have
Yeah,
set
okay.
or not this time, or you, I think you will get the answer correctly.
Yeah.
I'll just give you the solution so that it will be better for you to work it out later.
Okay.
So when solve with this also, I have a question similar to finding
This,
this
okay,
value.
okay,
Yeah.
okay.
So you're
This
given
might
four
would have
data
been to go to the big three and then do it.
Okay. Here also it's simple. In weekly, only one change is that in our weekly least square we add
One.
a column of one.
Yeah.
Because we will have only two data points, no, only one data point, x and y. So here
Okay.
x is x1 and x2. We have two values here.
So you don't need to add the column, right?
You don't have to add the column of ones here.
Okay.
So you're given two data points and their corresponding labels. So you use this linear regression and find this optimal W star using analytical method. So why this is actually the basic formula using that X inverse.
Okay.
So your W star is X transpose X inverse into X transpose Y.
Okay.
So actually in discourse also we had a question, but this is actually the correct answer you can verify.
Okay.
So we have X's 1, 0, 2, 1, 3, 2, 4, 2, 1, 5, 3. So you can, I hope you can multiply this X transpose X and X transpose Y. So at that time you will get this W star is 1.5 minus 0.0.
Yeah.
So this is the answer. This is straight away calculations.
Yeah. And then one question, somehow that X in the inverse, because it was covered in math too, how to find the inverse of a mathematics matrix, right? So I am more comfortable just putting it on the other side.
Okay.
XTX W star and then equal to XTY, and then write the equations in terms of W star.
Okay. So
solve
you do it in our
that will work, right? Will that fail anytime? Will that fail anytime?
Yeah, that will work when you have this two data points alone in your X. At that time, it will work definitely. Because we have only a matrix of size 2 cross 2.
No, but even now it will work, right? Because WTX is still 2 by 2.
No, if you have the X is 3 data points, what will happen? See, imagine here you have, say for...
no, but even if we go down, XTX is still 2 by 2, no?
Just a second, which screen are you seeing now?
No, if you go down the solution, XTX is still 2 by 2, right?
So here, no?
Yeah.
Is my solution screen is visible?
Yeah, it is visible. I'm seeing that screen.
Okay. So here, no, X transpose into X.
That is a 2 by 2 matrix.
Yes, sir. So what I'm trying to say is, if you have, let's say 1, 0, 1, another one column here.
Okay, 3-dimensional. Okay.
So at that time, what will happen? So here, 1, 2, 0, 1, and 1, 3. So at that time, you will get a 3-dimensional value.
Yeah, 2 by 3. Yeah, that will become an issue. Yeah.
And more number of points. So when you have more number of points with more number of columns, at that time we will have an issue with this linear solving. We cannot go for solving them with the simple linear equations. At that time, you're finding the inverse may be useful, but for exams, we won't ask such long inverse.
Okay, so here also I can put XTX and then I'll get 2 W star, because that is how we solve for week 3. So that's why I think
at that time we can solve.
Yeah,
otherwise, you can also augment your unity matrix, and then you can identity matrix, and then auto you can find inverse. You can go for row reduction. Do you know that step to do that?
No, I know only that thing, cofactor, and that method only thing I know.
Okay. So there is also one more method. So you have a matrix here. We have this X transpose. So we are to find the inverse of this matrix. Now at that time, what we can do is you can augment it with the identity matrix 1, 0, 1, 0, 1. And then what you can do is you can reduce the row here. You can start reducing our rows and make this matrix here.
Okay. We read it. Yeah, we read it in math. I think. Yeah. Okay. 1, 0, 0, 1, and the left side becomes the.
Yeah, this becomes identity matrix, and the right side value you will get as inverse of this matrix here. That's also simple. So first,
that is simple. Yeah.
Okay. I hope you can solve it. No, at that time also you will get here 1, 0 with some 4 reduction steps. You can get the answer as like this. No?
Yeah.
So here you will get 18 by 29. So that also we have. And here it will be minus 31 by 29. And so I'll just mention it here. You can note it down and then you can also
Yeah, I
work
will.
it out
Yeah.
later.
Yeah. So that is actually
That is
simpler than
also-
finding that cofactor and all that. Yeah.
Yeah. Without calculator also you can do this. No,
This.
simple.
Yeah.
So this is your X transpose X inverse.
Okay.
Okay. This is also a method for finding the inverse.
Okay.
Yeah, for 2x2 other tricks are also there.
Yeah.
Like this changing the off diagonal element.
Changing. Yeah, correct. ABC.
Oh, okay, I can see this. Yeah, okay. By the sum.
Yeah.
Okay, that 29 I have to figure out. I think 29 is
That is
Determinant.
Determinant. That is the determinant, right? Yeah. Okay.
Yes. That you can also do.
Yeah, you can go with that trick 1 upon AD minus BC. This
Yeah.
principal diagonal minus off diagonal multiplication, and then interchange the off diagonal and put the signs.
Yeah.
It's the easiest trick of 2 by 2.
That is also.
Okay.
Yes.
So that will
So
work
that is-
even if the thing is not symmetric, right?
Yeah, for 2 by 2 it works.
Yeah. There is no condition for being symmetric matrices.
Okay.
For that,
So you just have to interchange them. Yeah. Okay. 31, 31. Okay. Okay.
So once you found it using this analytical method, then we can apply this gradient descent optimization. So here I'm initializing your weight value for the first time step to be 0.1 and 0.1. So for the first iteration, you have that you have to calculate that gradient value, right? So what is the gradient value? So gradient is simple. So already you have calculated this X transpose X and X transpose Y here. And so gradient is simply you have to multiply with this your W, that is initial value, that is 0.1 and 0.1. That vector, if you multiply with the X transpose X value and subtract it with the X transpose Y. So that's how you will get your gradient value. So if you solve the first sum now, you will have values for this matrix multiplication and this matrix multiplication. So here W is 0.1 and 0.1. So here you have a 2 by 2 matrix and minus this 2 by 2 matrix. You can take it from the previous question. And then you can solve it to find the gradient of the function. So once you found the gradient value also, then this question we have asked to find what will be the value of the weight at the iteration, second iteration at time t is equal to 2. So here learning rate is 0.1. So your formula is simply you have to subtract this learning rate multiplied by your gradient of the first step. And then with the W1. So you will get your W2. Is it okay? Hello? Hello?
Sorry, I was speaking on mute. Yeah, I get that.
Oh,
Okay,
I
this is
see.
this is covered in the lecture, but except that the gradient was put as a thing. I'll have to remember that and then use it. Yeah.
Okay.
And my notes, I don't see that learning rate, but the NT, but I might have just missed writing it down. That's fine. I will check that.
Okay. Because also this learning rate, no, it is actually.
It's always, I know that anyway, that's how gradient descent works anyway.
Descent works, yeah. So when we move on to next is simple, you have a rectangle here. So a rectangle has a perimeter of 20 meters. So there is a rectangle here. So we have to use this. So this perimeter is 20 meters. So using this Lagrange multiply method, you have to find what is this height and what is this width.
Okay.
This height and width, which will maximize this value.
Yeah. Okay.
So
okay, I'll have to. This will take me time because always these questions I have a bit more time. Plus, I will do it the brute force method. But the Lagrange multiplier, I'm trying to see what is specific about that method that needs to be applied here. Yeah, I think I don't know that. Yeah, I'll just go with reading the solution and then I'll try to understand it.
So what is your perimeter formula? That is your x into y. So
yeah, okay. 2x plus 2y equal to 20.
20. And then we can use this. This is our optimization formula, x into y. And this is our constraint equation. So
that is how Lagrange comes. Okay, we change it that way. Okay.
Yes. So you have to solve the equation of deriving the first derivative of this function. So del of f of x comma y is equal to this your multiplier, no, Lagrange multiplier, lambda into this g of x comma y.
Okay. So this will.
Del,
Okay.
I
So of
missed
course
it.
the
Here it's also del. I am missing the solution.
del g. Yeah.
Del g of f of x.
XY.
Yeah. So when you have two variables x and y, so for first variable, your dou f by dou x equal to lambda into dou g by dou x. So only one constraint you have, so lambda.
Yeah.
And your second equation is with respect to the other variable y. So dou f by dou y is equal to lambda into dou g by dou y. So you will get two equations with respect to lambda here. So when you differentiate this function with respect to x, you will get y. And if you differentiate with respect to y, you will get x. So y is equal to here lambda into 2x plus 2y minus 20. So at that time, you will get 2 lambda. So y equal to 2 lambda. That's your first equation. The second equation, x equal to 2 lambda. So here your lambda is equal to y by 2. And here also your lambda is equal to x by 2. So both lambda should be equal. So at that time, you will get x is equal to y.
Yeah.
So when you have this x is equal to y, you substitute it in this equation. And so when you put it here, you will get 2y plus 2y equal to 20. Therefore, 4y equal to 20. Therefore, y is equal to 20 by 4, that is 5.
Yeah.
So when you have y as 5, x is obviously equal to
5, and then lambda is 2.5.
lambda should be half of them. So 5 by 2, that is 2.
Okay. So this is the Lagrange version of. This is actually a 6th standard problem. Yeah, but I understand the.
Example, how do we use this Lagrange multiplier?
Okay.
So this is about some conceptual understanding for the primal and dual. So which of these are correct? No? So dual of a dual is primal. This is a correct statement. Why? Because when you have a dual,
it is a correct statement.
It is a correct statement. All of these actually are the correct statement. When you have a dual problem, you are going to take a dual from a dual problem. So you consider that dual as a primal, then you are taking a dual of this primal. At that time, what you will get? A primal problem.
Okay.
So that is, you have a primal problem here. So from primal, you will get a dual. So now what I'm taking is from this dual, I'm once again going to take a dual. At that time, this will lead to a primal problem.
Okay.
Because imagine this is a min problem.
The other one
your
is
min will is a max. No,
max.
Minimizing will become a maximizing. Now for maximizing, I'm going to apply a dual.
Oh yeah, in the tutorial, in the tutorial there is an example of this, no?
Yeah, in tutorial we have an example. How do we interpret dual from a primal?
Yeah. Okay. That it gets changed. Okay, I will watch the.
Okay.
So the tutorial is very important in this.
Yeah, if you watch tutorial, you can answer these questions later.
Yeah.
And also that KKT condition question also you can solve if you watch the tutorial.
Yeah.
So here also I have given a table for the possibilities in
the last table, right? The very last part. Yeah.
If you go through that correctly, means you will get the answer to these two answers. So here the second statement is if either the primal or dual has an infeasible solution. So it does not have a solution. Infeasible means what is the meaning? It does not have any solution.
Yeah.
Then the value of the objective function of the other is unbounded. So that is true, no? Because if you have watched the tutorial, I will have a graph.
Yeah.
At that time, see if what is the meaning of unbounded. So unbounded is when your value of this is our x and this is our y.
This is a greater than equal to condition. Yeah, there's no bind. Yeah.
If you have a say, let us have some condition like greater than or equal to 20.
Yeah.
This is our constraint, and if you want to maximize this x over some that function to be f of x, let us have it like that. So at that time, what happens? Your selection of this x can be
anything, infinity,
because it is,
right?
it is unbounded.
Yeah.
That is right. So the solution, when it is in an infeasible solution, the other should be, the function should be unbounded.
Yeah.
So that is the two option. And the second one is, the third statement is if either the primal or the dual problem has a solution. then the other also has a solution.
Solution. Yeah.
And their optimum values are equal.
So this is the strong duality.
Now this is strong duality holds. So when both the primal and dual has a solution, means what happens? Their optimal values are same. So that is what we had a graph like this. So if your f of x is like this, and if your dual is function, so this is your say if your primal, and this is your dual. So let us imagine a condition like this. No, they both meet at same point. That is their value statement still. And the fourth one is if one of the variables in the primal has unrestricted sign, the constraint in dual is satisfied with equality. Actually, this statement is somewhat research in primal and dual interpretations, because in tutorial also I have covered if you have a constraint with greater than or equal to sign, then it is in, if it is in primal, what happens is when you convert this into a dual problem, this changes to less than or equal to constraint.
Yes.
Okay. But here what happens is when you have in primal, when you have equal to condition, that we did not deal in tutorial, because in class also we have not dealt it.
Yeah.
So in primal, what happens is when you have an equality constraint, at that time your dual variable becomes unrestricted in this time. You cannot restrict, because when you have an equal to sign in primal, it should be converted into two different equations. One with greater than equal to, and another one with less than or equal to.
Okay, so the unrestricted sign basically means this. I was thinking of negative positive.
Yeah, no. It is why we get this, because this condition, this equality condition will transfer into two inequality conditions. So
Okay.
at that time, you cannot restrict the sign because of the variables. See, because if you have that variable, say for example, the constraint is x1 equal to 0, just an imagination.
Yeah.
At that time, this equal to 0 means this is transferred to either it should be greater than or equal to 0, or it should be less than or equal to 0.
Okay.
Agree, you know? So at that time, what happens is, if it is to be greater than or equal to mean, it should be a positive.
Okay.
If it should be less than or equal to means, it should be negative. So both ways are possible. So it is restricted. We cannot restrict the sign of the variable. So that is why it is unrestricted.
Okay.
So that is the reason for this question. So this is also a true question, true statement. So this is a problem related to the objective function.
Okay.
Can we read it? So Rahul is a consumer who wants to maximize his utility subject to some constraints. So his utility is he consumes two goods, X and Y.
Yeah.
So the function is the product of their goods. So that is X into Y. So that is going to be his subjective function. And his budget is only ₹1,000. So per unit price of goods, X is 15 and Y is 20.
Yeah.
So just we have to choose the optimization.
Yeah, B, right? Yeah. B is correct.
To maximize this product, and so this is from this per unit price.
Yeah.
X and Y, and his budget is ₹1,000.
1,000. So it has to be 1,000. Actually, less than so. Yeah, so equal to 1,000, but I wasn't sure why less than equal to will not come, but that is okay. So we'll just go with the equality condition, because you don't necessarily have to spend that much, right?
Yeah, his budget is actually ₹1,000. He has not less than or equal to, or nothing like his budget is less than 1,000. He has a ₹1,000 budget.
Okay.
So he wants to buy these two products for ₹1,000, not anything less than that.
Yeah.
So therefore it is equal to same. So for this function, I think next question is you have to write its equivalent Lagrange. That is also simple, no?
Yeah.
If you have gotten this correct, no? You have
X,
this
Y, yeah, minus lambda into 15x.
Into x plus 20y.
20 minus 20 minus 2,000. Yeah.
So that is the answer. So your option C is the Lagrange value. So
this is more like a solve within sector question. Step by step, no?
Okay.
Yeah. Okay.
And so this is using our KKT conditions. Why? Because we have that inequality. And one thing why we don't have this for Lagrange, no, we solve only for equality constraint problems. Do you remember in lectures?
Yeah.
So when we go for inequality, we go for
KKT.
KKT conditions. Okay. So you have given with one function. Now this function is having two variables, x1 and x2. And we have two constraints, g1 and g2. So you have to identify which is the optimal solution. And this also, if you watch the tutorial, it is easy for you to solve. Now, let's go through it once.
Okay.
So when you talk about KKT conditions, we have 4 conditions. So whenever you are asked to solve such problems with KKT conditions, you can first write down all the 4 conditions.
Okay.
So after writing down those conditions, you will definitely get a way for finding this x1 and x2. Because to find our optimal solution is x1 and x2.
Yeah.
So here.
Yeah.
And so to find is x1 and x2. So since we have 2 constraints, so we have constraints. So how many Lagrange multipliers you have to use? That is your first thing. 2.
Yeah.
So because we have
Two
G1
constraints.
and G2.
G2.
So these are all inequality constraints. Remember? No?
Yes.
These are
Yeah.
inequality constraints. If you have equality constraints, the formula also differs. You have to apply. So for these 2 inequality constraints, you have U1 and U2.
U2.
Multipliers. Okay. So our stationarity condition, this is our first condition, no? Derivative. So in lecture, Sir would have mentioned like a del of f. No? That just I have written it in terms of partial differentiation. That's all.
Yeah.
You will get 2 equations related to x1 and x2 because you have 2 variables. So for the first equation, what you'll do is you have to differentiate with respect to x1. So your equation here is, you can also solve x1 square
plus 60x1 plus 60. Yeah.
So x1 square plus 60x1 plus x2 square. So what we going to do is we have this equation for f of x, and let us write for also g of x.
Yeah.
So g1 is x1 minus 80. So that is simple. So x1 minus 80 is equal to your g. G1.
Yeah.
And G2 is x1
plus x2 minus 120.
So that is your G2.
Yeah.
So what we have to do is for
plus,
first,
yeah. First one will be 2x1 plus 60 plus u1 plus u2.
Here we have summation. So
yeah.
What happens? You have to do both G1 and G2 with respect to x1.
Yeah.
And then you have to apply this multiplier. So if you remember this formula, you have to take it correctly.
Yeah.
So J corresponds to U and G.
G.
The denominator part, you have Xi. I is 1 and 2. So you have 2 equations. So this is our first equation. Second equation, we go for differentiating with respect to x2. So that is, we get 2x2 plus here there is no x2 term. No?
Yeah.
G1. So
let's say 0 u1. Yeah, 0 u1 plus u2 equal to 0. Yeah.
U2 equal to 0. So that is our stationarity condition. The next is our complementary slackness condition. So it gives us our inequality constraint. You remember?
Yeah.
Because even if you have equality constraints, you cannot have this slackness conditions. In this problem, there is no equality constraint. But in case if there is any equality, you should not have that only with respect to inequality constraints.
Yeah.
So u1 into x1 minus 80 equal to 0. So the second is u2 into x1 plus x2 minus 120 equal to 0. So other 2 conditions are for our verification purposes because we cannot solve any values from here because it is a inequality value. It is either greater than or equal to 0. We can check after finding this x1 and x2, we can check whether they are satisfying these 2 conditions.
Okay.
That's why we cannot do any checking. Okay. So simply I have written the equations.
Okay. Here. But now the first one itself is enough, right?
Yeah, first 2 conditions. So once you have framed this stationarity and complementary slackness,
no, but
what you can first do?
In this thing, stationary condition itself is enough to solve.
So here, well, how you can get this enough? See here, it is only
2
equations with the 3 unknowns.
Yeah, okay. Sorry. Yeah, sorry.
There is no u1 here, you can directly solve it.
Yeah.
But here it is x1.
Yeah.
x1, u1, u2. And here it is x2 and u2.
U2. Yeah.
So you cannot get some direct relationship from this equation. So we go for this complementary slackness.
Okay.
So here, if we take this first condition, x1 in u1 into x1 minus 80 equal to 0. So we already saw no. Either
U1
it is
U1 0 or x1 equal to 80.
minus, that's it. So here we can have first condition. So we have to, when you have two possibilities, you have to check both the possibilities.
Okay.
So if you have this case one and if you can get some solutions, but you should not leave out this case also. So that is why you have given some practice problem.
Like even in the previous week, you get 4 cases, you have to check them one by one, right? So similar thing. Okay, yeah.
Similar thing. So you have to check whether all these cases and whether they satisfy all those 4 KKT conditions.
Okay.
So this is simple. If you go and substitute in the formula first one, that is our stationarity condition. So you will get a value for x1. x1, you can have it as minus u2 by 2 minus 30.
Yes,
if you solve it, you will get it.
Okay.
And now we have this x1 value. So in second stationarity condition, this one, you can substitute for this x1 value. At that time, you will get some equation for x2.
Yeah.
Okay. So
and
with
then
both
you put
these
it,
values, we can use those 4 equations interchangeably. Then we can arrive at this u2 value here. u2 is equal to 0 or
minus
is
150.
Once again, here also we have 2 confusions. So first we will choose u2 equal to 0.
No, u2 should be minus 300, right? Here, the next one, not minus 150.
Here.
u2 by 2 minus 150 equal to 0.
Yeah, correct. Anyway, it will violate the condition.
Okay.
I'll change it. So here it is minus 300. But this will, once again, your values will be increasing. At that time, if you check means, it will violate the condition.
Yeah, that's why you have, this is like you always, right? This is also one of the possible options.
This is also one of the possible options, right? And then you can also check it. No?
Yeah, one of the answers is this. So if you don't,
one of the answers, yeah. You can get the answer, but if it is not
positive, you
satisfying,
have to,
we cannot choose it. So like this, if you proceed further, so the first condition will fail. That is u1 equal to 0 will not give you any answer. So we are moving on to the second condition. That is x1 equal to 80. So here, from here, this condition, so this is not good. So this is not giving us optimal values. So we are checking for x1 equal to 80. So at that time also, similarly, you go and repeat the steps. No? Same.
Yeah.
How we
but
can
x1 equal to 80, we can go to the original condition itself and get it very simply.
From the condition also, I can get it. In any approaches, you always go to see steps.
Okay.
So you can, which one is suitable, you can find.
Yeah.
So at that time, you will get value.
Yeah.
You get u2 as this minus 1. You go and substitute it in the previous equations. And once again, you will get this value for a contradiction value x2 and x2 minus 40. At that time, you first select x2 equal to 0. At that time, what happens? Your values will violate the condition.
Yeah.
You can check it.
Okay.
And when you substitute x2 equal to 40. So now, if you find all the conditions are satisfied for x1 equal to 80 and x2 equal to 40, the conditions are satisfied. So once you see the conditions are satisfied, you can finish the problem because we can find all the conditions are satisfied.
Yeah. So that way,
there are no other, but there should not be no other possibilities.
Okay.
Because here there is no other possibility. We have checked all the conditions.
2 by 2, yeah, 4 possibilities. All the 4 possibilities we have checked. Yeah.
Yeah, checked. So this is that's why we have given options for you here. So what will you do if no options are provided? If it is a numerical answer type questions, at that time you have to enter your value for yourself. So this is your correct answer.
Correct.
So these options we check by ourselves.
Yeah. The thing is that here the biggest thing is that the approach, so that you don't get confused. You have to write the KKT conditions very clearly, number them.
Yeah, correct.
right? And then
Yes, sir.
because there is no particular formula that you always go put the 2 into 3 and 3 or 4 in 5. Depending on the
No,
condition, you have to
no.
apply the right one.
Yeah.
Right?
Yeah,
So
we cannot say that substitute directly in complementary slackness. We cannot say.
yeah, do that. So you have to do that. So that way, initial conditions, you have to write them and number them clearly,
Yes.
and then see what you use and
Yeah.
what you use for checking. Okay.
Yeah. Because no, some functions. So this function is in power 2. No? That's why you can get first derivative itself. You have some x1 and x2 here.
Yeah.
What will happen if you have simply x1 plus 60 x2? At that time, if you take a first derivative,
It'll be
x1 will equal to
vanish.
1.
Yeah.
Yeah, it will. Your variables might vanish in stationarity condition, but they will be there in complementary slackness.
Yes.
So at that time, we cannot give a strong foundation like start with this step.
Yes.
So first you have to write down these two conditions, this stationarity and complementary slackness, and then you can find. And one more thing, if it is asked in numerical answer type questions, right? Enter the value, optimal value. At that time, you cannot miss out any condition. You cannot.
You have to go through all the conditions. Yeah. So don't take shortcuts. Basically, work out everything.
Some
right?
minor value changes might not satisfy this primal feasibility.
Yeah.
At that time, it may miss out. So if it is asked in numerical type, answer type means you have to carefully work out all the possibilities of x1, x2 and the Lagrange variables. Because they should be greater than or equal to 0 at that time. So that's all with the practice. I hope in graded also similar questions are asked. You can carry out in graded also.
Okay. That way, yeah, I think here watching the last two lectures, last two this thing, KKD, because KKD is a pretty large concept. I know that it was covered well, but you have to read it multiple times to understand it.
Yes. How do we get the conditions?
Yeah.
And because we can also ask problems like convert the primal into dual and then find the optimal solution.
Okay.
Some kind of problems are also maybe like asked like that. But for practice, I put it simple so that you can easily check for yourself. So that's all about the practice problem. So I'll share that solve with this is not pretty difficult thing. Just some concept oriented. I'll share that.
Okay. But I think this 3 concepts are more difficult than the applications. So.
Okay. Any concepts you want to go through?
No, I think it's fine. I just have to read that. I'm sure anyway, this is going to come more in MLT also later, right? So this is going to be a...
In ML techniques now, what happens, you will be introduced through algorithms in more programmatic approach.
Okay.
You will have definitely how do you solve this algorithms through code. So that is the main focus for ML techniques and practices.
Okay.
There you won't have this kind of completely
the foundational parts, mathematical approach. Okay.
I'll share my screen.
Yeah, you will get better visualization in this.
Yeah. Okay. So this is simple actually. Some concepts related to convexity only have taken.
Okay.
So which of the following sets are convex, closed, and bounded? This actually you can, if you have knowledge about how these functions will work. What I thought initially was I can ask you to plot this function and you tell me the answer.
Okay.
So that's why I chose this question.
What does closed mean here?
What is
closed?
Closed in the sense, if you have that open and closed interval. Do you remember? If you
okay.
I cannot write in the screen. Now, just for example, if you have some set of numbers from 0 to 5. Also, when you say the set is open, it does not include the endpoints.
Intervals. Okay, so that is what closed means.
Okay. Closed means it includes the endpoints.
Okay.
So, how can you tell whether it is closed in this equations? With respect to that equality symbol. if you
Equality
see
symbol,
here,
right? So is greater than
yeah.
equal to will be
greater than or
closed.
equal to will be closed. And like that you can guess. And less than or equal to will also be closed.
Yeah.
But if it is open means greater than alone,
Yeah.
that is an open. That itself will cancel out that value.
Yeah. And bounded means less than equal to. Greater than equal to is not going to be bounded.
Bounded. Yeah.
Right?
Yeah,
Yeah.
correct. Bounded means if it is, you can get any value greater than this value. At that time, what happens? It can extend till infinity.
Yeah.
Both in negative and positive sense.
Yeah. So A is definitely all, right? Convex, closed,
A
unbounded.
is convex. Yeah, correct. A.
Right? And I can't think of anything else which is satisfying all the three conditions.
Okay. One more is C.
C is convex and
convex.
closed, but not bounded, right?
No, it is bounded.
Oh, bounded because the upper condition is bounded. Okay.
Because for variables x and y, no, we are having a bound. X should be greater than or equal to 0.
Yeah.
Their combination is less than or equal to 2. At that time, it is bounded.
Bounded. Okay. And then
So others,
D is not bounded. E is not bounded.
bounded.
F is the objective is not bounded. The conditions are bounded. Yeah, this is xy greater than 1 means it could be anywhere. Yeah.
Yes, correct. So A actually,
Yeah.
so I had a visualization. And do you see my screen? Which screen
Not yet.
is visible?
I can see only the solution screen, not the GeoGebra screen.
Okay. Share my screen, I think. Just a second. Now is it visible?
Yeah.
See the function one by one.
Okay.
So this is the first function. X square plus y square is less than or equal to 4.
This is a
So
unit
this is
circle.
a,
Yeah, units.
uh,
Yeah, so
this
not
is
unit
a
circle, circle of
not
radius.
say,
Yeah.
circular radius too. So this is a closed and
Yeah.
And the second is simply a linear line. It can be a convex or it can also be concave. That is the linear function.
Yeah.
Third one is this x plus y is less than or equal to 2. At the time
That's
here
why it
it
is
is
bounded, yeah.
unbound. And for only y is greater than or equal to x square.
Yeah.
So this is a convex set, but what happens? It is not bounded. It is unbounded. It has some infinite extension. Last thing is xy greater than 1. It's also not closed, it is open. It is greater than. So that's why I wanted to have this illustration. But from equations also you can easily identify.
Right, that, yeah.
So the second problem is f of x is a function 3 plus x square plus x and g of x is e power minus x. So what can you say about their composition?
No, e power x square is definitely, e power x is definitely convex. E power minus x is not convex, right?
Anything actually to the power of x is convex, g e power minus x. It is in the positive side, it is in the negative side, but it lies on the first and third quad. When you have a squared value, e power minus x is squared, that is concave.
Okay. And so then composition, what can I say about the composition H1 FOG, H2 GOF? FOG, H1 is convex.
H1 is F of G.
Yeah, so that way F has to be convex and
yes.
non-decreasing.
Yeah.
So that is true.
Yeah.
And
here it is G of F.
Be linear. Yeah. So that way FOG is convex. G of F, I don't think it is convex because the linear thing is not satisfied. So I don't know whether from the information I remember so far, I can't figure out clearly G of F is not. It seems to be not convex.
Yeah, it is a concave function.
Okay,
because
so that way
exponential of x power, you have a squared power there.
Okay.
Okay. So we have graph also. You can.
So that way the first answer is correct. Right? H1 is concave and H1 is convex, H2 is convex. H1 is convex that I can clearly see.
H1 is convex and H2 is concave. Actually.
Concave. Okay. That is.
So these are our functions. Can you see the functions? So is this plot visible to you? This is f of x and this is g of x. Hello?
Yeah, the screen is visible. Yeah.
Okay. So sorry, your audio is not clear. That's fine.
Yeah, I can see it. Yeah. My because my broadband is not working correctly. So
okay. So now let's finish it. And so when you have this f of g of x, so simply f of g of x, if we have means that is a convex function.
Convex function.
So g of x, it is a concave nature. See, you zoom in, you can see. Its exponential power also square of x is there.
Okay.
So at that time, see, you can see this is a concave function.
Concave function. Okay. It's a small function. Okay, because the very small values. Yeah.
You have to zoom in and then you can verify that.
Okay.
So H1 is convex and H2 is concave.
Concave.
So on the third problem, so you consider the following problem. X plus y subject to the constraints. So we have 4 constraints. X is x comma y greater than or equal to 0. The first constraint is minus 3x plus 2y less than or equal to minus 1. X minus y less than or equal to 2.
Yeah. So this is going to be bounded.
Is the feasible region bounded or unbounded? Yeah, it is going to be
bounded.
Why? Because we have this x value should be greater than or equal to 0. And if you plot this one, you can see. Okay.
No, I am trying to do it without the plotting because we don't have the GeoGebra. Okay. But yeah, that's okay. I can understand because from the lecture, yeah.
The lecture itself we can see.
Yeah.
Yes, sir. This is just to give us an idea whether how this feasible region will be.
Okay.
And that for that why I just had this one. So if you see here, these are the 2 constraints: x greater than 0, and this is y greater than 0 is in the upper quadrant.
Yeah.
And this is one constraint: minus 3x plus 2y less than or equal to minus 1. Green color. Yeah. And the 4th constraint is this is x minus y less than or equal to 2. 3. So this shaded region here, this is actually not bounded, it is unbounded.
Unbounded. Oh, because it can go.
It can, this is the common region. You can see my arrow here.
Yeah, it can go to infinity also. Okay. Less than equal to 2. Okay. That's all right. Yeah. Okay.
This can go till, so if you have a condition like any equation that is in this direction, like x plus y or something like in this direction, means it will be bounded.
Bounded. But since it is x minus y, it can go unbounded.
It is unbounded. So only one more problem, that is
okay, so this answer was wrong. Okay, my initial answer was wrong. Okay, I have to understand that.
Yeah. It is bounded.
Yeah, it is wrong.
Not bounded.
Yeah, it's not. Okay.
But here I just wanted to calculate using this gradient descent approach. Given a same, like how we did in practice problem.
Even the practice assignment, I have to get familiar with it because that's something I have to practice. So maybe we can today because I think it will take me more time.
Okay, sir.
We can skip it. But I think the answer, I think we can take the same approach and do it. And it's again 2 points only, right? Not the
it is 2 points. Yeah.
So
why I had is because when you use least squares, you will be adding this column vector 1.
Yeah.
So in order to avoid that confusion, I had it in this session.
Okay.
You don't have to add any such columns of 1 here. It is basically you can consider this x as a vector matrix.
Okay. So for 4, so I would theoretically, so we have to write x as 1, 2, 2, 1.5, 2, 3, 3, 4.
Yes.
Take x transpose of x. X transpose x into x
transpose. Yes.
Xt into x.
Xt into x.
Xt into x. So that will be a 2 by 2 matrix again.
Yes, sir.
Right. That you get the inverse of it. Then X transpose of Y, you have to get that. And then
no, sir, actually here, no, you are not asking analytically. You don't have to do that inverse computation. In this question, I have just asked, use gradient descent update equation. And then you find the value of this W at
I'm sorry, I
iteration.
didn't get that.
So here now, you do not need to take any inverse computation. I have not asked for any analytical solution.
Okay.
It's simple. You just have to find the gradient value, del F.
Okay. Okay.
Okay. So for analytical method only, get direct optimal W star. For that, you need that inverse computation. For our gradient descent rule, we compute the gradient value, del F, that is equal to X transpose X W minus X transpose Y.
Okay.
And then you find that gradient value. So use that gradient to find the updated weight value.
Updated. Okay. So we get the gradient value, then 0.1, 0.1 minus the learning is also 0.1.
Yeah.
Right? Minus 0.1 of that matrix will be the value at t equal to 2.
Yes, sir. Yes, sir.
Okay.
So that's it. Since now in solve this, if you take inverse computation, it may take time. So I didn't ask for this analytical method.
Okay.
So that's what. So you find the gradient value. So you'll get one matrix answer and then use it to find the updated weight value.
Yeah, XTX is this, XTY is the 2 by 1 matrix. Yeah. And then okay, just that. So that way, okay. So we have to be very clear about the method, right? So you don't need to go to the inverse.
Yes, sir.
Just apply this. Yeah. And here we are doing full gradient descent, not stochastic, because there are only 2 points. So you don't need to go.
Not any batch size. No.
Yeah.
We have only 4 data points.
Yeah.
We have 4 data points, each with 2 features.
Yeah. So that way you don't need to cut down the features, right? Yeah.
Yeah. Basically, now when you have some 100 or 200 data points, at that time you go for stochastic reading design.
Okay.
That's all about the solve this. I didn't go much about the KKT because it takes a lot of time to solve it.
Okay.
I hope this KKT conditions also.
No, KKT, that is, okay, what I see is something that is simple to understand, but you have to practice at least 4 problems, only then you will get it.
Yes, you have to do.
Right? KKT, because of it can get confusing, no?
Yeah, so that way for graded, you try to solve that.
Yeah, so the practice assignment, I think that solution is that the question is very nice. So if I do it, I think I will get enough practice. Because the activity question, obviously, they didn't test, they test only the conceptual thing that I could answer.
This it is put in that way.
Yeah, yeah.
You don't have to use calculations for activity, just to remember the concepts covered in activity. So that is why we have those activities.
Okay, ma'am. So I think I'll get it. So this should be fine. And then the SWI is very useful. The last question particularly is useful to get that gradient descent method practiced. Yeah.
So that's all about week 9.
Okay. Thank you so much. Thank you again for the time.
Okay, thank you, sir, for joining today.
And then quite a few students have said in discourse that they find the sessions useful. They watch the video later.
Yes, sir.
So hopefully some of them are using it. That's why I requested. Thank you for accommodating.
Okay, yeah, that's actually very so nice of you to ask this now. Because yesterday I thought of covering those activity and practice.
Wednesday, because what I have done is I have marked this. I'm a freelancer, so I have marked Friday 11 to 1. I have marked as busy in my calendar for this term. So that Friday 11 to 1 session I will always be able to attend. That Wednesday was 3 to 5, right? It was a different time session. I couldn't attend to that. So
due to this Deepavali, we have to change.
No issues. Yeah. So that way, all the Wednesdays, all the Friday sessions, as well as the evening sessions, I should be able to attend, and then hopefully I'll be able to participate. Thank you.
Okay, sir. Okay. Thank you so much for your participation.
Okay. Thanks for the time again. Thanks, JP.
Thank you, sir.
Yeah. You will be closing the call now, right?
Yeah, we'll be closing.
Okay. Thank you so much.
Okay. Thank you, sir.
Thank you, sir.
Thank
You are welcome. I should thank you for the
Thank
time.
you.
Thank you.
Okay.
Yeah,
So
because
anyhow, revise it in revision session also we have before quiz 3
I
all
think
these
he's
weeks.
I think he
What?
left the session.
Okay. So anyhow, we'll also have a revision session before quiz
Yeah,
3
yeah.
for all these weeks. At that time also we'll have to cover all 8 and 9.
Yeah,
We'll
yeah.
have some more problems related to that our contents in that session.
Yeah, the thing was was the last session for week 9, no, and before this, not even a single week 9 session happened. So I think, yeah, it will
This
be
is our
very,
last session.
yeah, it will be very useful for people.
Yeah,
to
yesterday
revise.
also, Jimmy, I thought of no for activity and practice notes for in lectures. The SAT have not covered any examples in week 9.
Yeah,
So I thought it may be useful for the students if they attend the practice session. So thanks to actually Srinivasan sir for joining and
yeah,
discuss those problems in week 9.
yes. And I was also expecting at least they will join week 9 activity session, because since there will be only a single session for week 9, like activity
Yeah,
practice, and yeah, but unfortunately no one joined.
but it's expected due to the holiday.
Yes, yes, yes. That was the reason. Yeah, it's okay. I think we should.
We can close.
Yeah, yeah.
Thanks, Jimmy.
Thank you, ma'am. Amrita. Yeah.
Okay. Bye.
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 Bye. So you message in the group, or I
Yeah.
should? Yeah.
Yeah,
Okay.
I'll message him.
Okay. Okay. Okay.
Okay, bye. So, Vignesh, we are closed. We can close the session.
It's better to put it in the group, because
Okay.